Okay, so we're not doing the synthesis this time because it was recommended that what we should do is kind of do a review. Okay, so we're going to take a brief synthesis break and take a look at an example that was already solved by another person in the class or another group in the class. Okay, and there's a variety of ways to approach synthesis, and the one that seems to be making more and more sense to me is going through and using pretty much those three rules. Identify the changes that are occurring. So you go from here to here, reaction to product. Okay. Once you've identified the changes, then look at those changes and say which reaction does those changes. Okay. I don't mean reagent, I mean substitution, acid-base, elimination, addition, radical reactions. Okay. You need to have those general patterns memorized. Okay. If a reaction that does all of those changes, then sweet, you're probably doing it in one step. But what if you're missing something? Right? Let's say you're doing an elimination, but you needed to add a bond. Well, elimination doesn't add things. That means you're going to be doing it in multiple steps. So it's a question of what steps you then choose. Pick a reaction, doesn't matter what, and do that reaction. Okay? You now have a new structure. Go back to start one. Identify the changes from your new structure going to your product. Okay. Is it now a simple, oh, that's just a substitution? Do substitution. Okay. Is it requires more than one reaction? Pick one of the reactions and do it. What happens if you're wrong? You go back and you try again. Okay. Yes, that does kind of suck, but eventually you go back enough times that you stop picking bad reagents because you look up your chemistry quickly enough or frequently enough that you start to internalize and memorize how those pieces change. Okay? So what are the changes happening in this reaction? Okay. So does any reaction move a pi bond? No. So saying moving a pi bond becomes very problematic for me because that's not going to match anything.
Removing a hydrogen.
So we could break a pi bond, and then we can make a pi bond. Okay, and we should already immediately be saying, well, crap, this is going to have to be two reactions because those are opposites to each other. Making a pi bond is an elimination. Breaking a pi bond is an addition. Okay, so I already know there are multiple steps in this. Okay, what else changed? Okay, we removed a hydrogen and we added a hydrogen. So again, we have to be careful in our phrasing. We can't just pick up an atom and slide it across. Rearrangements are a possibility, but rearrangements are hard to immediately see. So don't assume rearrangement. Assume you're breaking and making again. See anything else? No, we're not losing a hydrogen overall. I would argue that's all of it. So making a pi bond, to make a pi bond, I would be doing an elimination. I need to break a hydrogen off typically. Okay, so those would be paired with each other. And the breaking of a pi bond and making of a hydrogen probably are paired with each other. So which of those two sets should I do first? Okay. To make a pi bond, I need to do an elimination reaction. So I have to think about my elimination reaction and say, well, what do I need to run an elimination? Okay. Well, what do I need? What does the symbol Lg mean? Leaving group. Do I have a leaving group? No. So can I do the elimination? No, I have to do the addition. Okay. So when I add, I'm going to be adding two things. Those two things will go where? Not quite, but you're going the right direction. We'll be breaking a pi bond. We're adding something to the structure. Where will those two things be added? Our tertiary carbon and the other carbon of the pi bond. That's what addition reactions do. We add to those two positions. Okay. Well, what do we want to add? What's that? If we add hydrogen, what do we get? So what would our functional group be? We put hydrogen in both those locations, and we now have what kind of a structure? An alkane. What is the reactivity of an alkane? Zip, zero, and zilch. Probably not a good idea. Okay, we could try HBr. Okay, where would that place the hydrogen? HBr is going to put the hydrogen on the the less substituted position, and the bromine will go to the least substituted. Okay. What you are confusing it with is radical addition. How would I know I was doing a radical addition? I would want the bromine out on this tail carbon. Do I want the bromine out there? Why not? Is that getting closer or further from chemistry of my product? It's getting me further. So I want chemistry sucking into the structure, not going outside. So I now have HBr added to the structure. Boom. Is that right? I don't know. See what happens. Okay. We now have to repeat question 1 again. Identify the changes. What's changing as we go from here to here? Lose bromine. Make pi bond. That's it? Okay, lose hydrogen. Oh, that's interesting. Those 3 together make up an elimination reaction. Okay. So where would we do our elimination? What do we need as a reagent to help us with an elimination? Or what could we use as a reagent to help us with elimination? A base. Okay. What hydrogen is going to get removed? The one that's going to form the most substituted double bond at the end of the elimination, which means we remove the hydrogen from the beta position to our halide, or the alpha position, beta position to our halide.
This part would be anti-periplanar.
We would have to have anti-periplanar. Do we have to be concerned about that in this case? No, why not? No stereochemistry specified, so we don't have to freak out too much. And we would end up with a new product. Well, that's cool. That did everything I wanted it to do. Loss of a bromine, make a pi bond, and loss of hydrogen. Do I have my final product? No. So what do I have to do now?
Another reaction.
I have to do another reaction. Well, what things changed? Okay, can I change the location of a pi bond? No. That kind of sucks. Okay, so I'm going to have to go through and run through the make and break of my pi bond, just like we did last time. Okay, kind of get the idea? Make sense? The reagents are secondary. Okay, and ideally, notice what reagents we're using. I'm using bromine as a leaving group. Why not OH? Bromine's a good leaving group, but OH could be made a good leaving group. Why not use OH? I can kind of accept because we'd have to protonate it. I can kind of accept easy to remember. OH acts as a nucleophile as well as a leaving group. That increases the potential for side reactions. If we run side reactions, do we get a high yield of the product? No. So we're trying to pick the simplest route possible. Okay. Notice the base even. Did I specify what the base was? No. I can figure that out later once I know what I'm aiming for. Okay? Questions about that?
So would you just basically repeat steps 1 and 2 to go from...
Okay, since you're asking, we'll go ahead and do that. So we need to do an addition. What do we want to add? Okay, let's add HBr. Where's the bromine go? Back to where it was. Sorry, Jen, you were wrong. Try again.
No.
No, NBS isn't going to work for us, actually. What is NBS going to do in the presence of an alkene? Radical substitution for a hydrogen? We don't want to do a substitution, we're trying to do an addition. Okay. But I like where you're going with NBS, we want to do a radical. I want to add HBr, but I want to add it in the opposite direction of where it should be, which means I should do something pretty radical. Add a radical initiator. Now what happens? I can put the bromine in the least substituted position, and the hydrogen goes to the most. Okay? You still need to know the reagents, but it's questioning how and where things need to go. Worst case, where should the bromine be? Where do you know it needs to be? It needs to be at that position. It can't be at the most substituted. So draw that and then guess for a reagent. Why not? You got something. Okay. Now what? We got to go from that bromine up to this guy. What things changed? Made a pi bond. Lost bromine. Lost hydrogen. All of that is something that is characteristic of an elimination reaction. So let's do an elimination. Let's add our base. Where does the base eliminate? It always makes the most substituted, and always being in air quotes, substituted pi bond, which is not our product. So we need a base that will selectively choose to go away from the most substituted position. Well, the most substituted position is substituted, meaning it has lots and lots of electrons. So what kind of base should we use? Something that's really, really, really big. A bulky base should now increase the yield of our elimination happening in the least substituted position. Are we going to get awesome yields? Probably not. But does it work? Yeah. Okay? Make sense? Notice, each step, what were we evaluating? I only wrote it down a couple times. What are the big things that changed? Tie that to a reaction. Okay? And then do whatever that reaction says. Don't worry about what the exact reagents are. Just, if I want to do an elimination, the product needs to be double bond. Has to be there. Okay? If I want to do an addition, what do I expect to not see in the product? Double bond. Okay? So you need to be super familiar with what the patterns are for each of those reactions. If you aren't familiar with those patterns, you're guessing. Okay? Which, I'm not going to lie, because I went through chemistry without really spending that much time memorizing them, you can luck your way through. Okay? Ideally, you do better than me. Okay? Make sense? Okay, we talk too much. Or I guess I talk too much. The next big section, I guess I put that in at the wrong point, was looking at the 1,2 versus the 1,4 conjugate addition. So when we talked about our carbonyl in chapter 17, we were using really, really strong nucleophiles, and we really only looked at the carbonyl functional group. But what happens if I bring a functional group close to another functional group? Well, they can affect each other. That's why we can take an alcohol and make it acidic by, how do I make this example alcohol acidic? What functional group should I put it in here? A carbonyl, and now it's a carboxylic acid. Okay? So bringing multiple functional groups near each other changes the chemistry. Okay? And oftentimes it's changing it through resonance. Yay, resonance. Okay? So if we go through and look at our conjugated carbonyl, we're taking a double bond, an alkene, and we're putting it right next to a carbonyl. What's the issue, or what do we notice? We have resonance. What is particularly interesting about that resonance? What does that look like? No, it does not look like a carboxylic acid. That looks kind of like an enolate. Okay? Why would this resonance be a common form? We're effectively forming an enolate. Okay? So we do have that active chemistry within that position. To get there, what happened? Yes, resonance, good answer. Give me another one. That is drawing, right? What happened in there? We have another electrophile. We have a positive carbon. Okay. Another electrophile means more locations where our reagents can potentially react. And we now need to evaluate where should our nucleophile attack. Should it attack the carbon, or should it attack, the beta carbon, or should it attack the carbonyl carbon? Okay, well, which one do you think it should attack? Okay, getting too specific in the answer, but yes. It's going to depend. It's going to depend on the strength of our nucleophile. If we have a really, really, really strong nucleophile, what is it going to try and do? The most positive atom possible to cancel that negative charge. Okay? Which of those carbons is more positive, the carbonyl carbon or the beta carbon? The carbonyl carbon. So our stupidly strong nucleophile immediately seeks out the carbonyl carbon, and we end up with the 1,2 conjugate addition. Okay? What happens if we have just kind of a weak nucleophile? Floating around, la-di-da-di-da. Okay? It's kind of stable, so it's only going to react if it can generate a more stable product. Okay? So we'd have to look at those potential reactions and see what's going to happen. We just brought up which one does it react with fastest, and which one does it react with to make the most stable product, i.e. kinetic and thermodynamic. Okay? So we have to be thinking about and approaching that. Okay? The big reagent out of chapter 17, yes, is what's known as the Gilman reagent. Of course, it gets somebody's name because we have a carbon nucleophile, and it does stupidly weird stuff by not attacking the carbonyl. Okay? So it gets a name. It becomes the Gilman reagent. Okay? Are you responsible for knowing what the Gilman reagent is? Yes. How do you make it? There it is. Okay? The more relevant question is, why does it attack the other position? Okay, so we need to be able to evaluate our kinetic versus thermodynamic. Here we go. So, I did not fix the color coding. This kills me. Okay. So, let's take a look at these. We've got the reactions drawn up there. Before we even launch into an energy diagram, let's try and decide our kinetic versus thermodynamic product. Which one's the easiest to identify, kinetic or thermodynamic? Okay. Where do you see something easy about kinetic?
Thermodynamics is technically the one more easier to identify.
Why is the thermodynamic easier to identify? What are you comparing?
State of stability.
A product, an actual structure. In the kinetic, what are you comparing? Kind of a harder question. The transition state. Where's the transition state drawn? It isn't. It is very difficult to identify the kinetic product because you're evaluating something that we don't ever draw. Okay? The thermodynamic product should stand out because we're drawing the product. Okay? So let's take a look at our products. What do you see as reactive in those two structures? Why the pi bond?
Has electron.
So does the oxygen.
Position of the carbon.
That gets closer. Why ignore the oxygen? What's that? They both have oxygens, and they both have the same number of lone pairs. Is there a difference between the oxygens? No. So that's useless to compare. So we could move to the pi bond. Okay? Because as you've noted, the pi bond location is in a different place. Okay? Where we have a difference, we can now try and identify. Why else should we look at the pi bond? Pi bonds are made up of electrons, fair enough, located in p orbitals. Where are p orbitals relative to all of the other orbitals? They're the highest energy. Which electrons should we use in a reaction? The highest energy electrons. Okay? So if we compare those two structures, and in particular the double bond, what can you tell me about the double bond? The bottom one is more stable. Why? We have a more substituted pi bond. Okay? which then means we have more stable, lower energy, and we have the thermodynamic product. Okay, well, if we're concerned about kinetic and thermodynamic, we now have a cheat, and the top one must be our kinetic. Okay, so something about our energy diagram would hopefully jump out at us and allow us to see how that worked out. So we can go through and look at the energy diagram all the way through and say, where does it change? Where does it set up? Okay, so let's take a look for the kinetic one. Okay, it's intermediate. So we'll call the top one 2, the bottom one 1. Compare the intermediates formed. Which one is more stable? Why should the top one be more stable?
Oxygen's bigger.
Oxygen is more electronegative. Interesting. Sorry, I had to pause because I was like, oh crap. Let's see why it's oh crap. Because if that's the case, what does that mean? Our kinetic one is lower energy.
What about the resonance structure?
Oh, interesting. When we look at our stability of our intermediates, we have to evaluate everything about them. What does the bottom one have? It has resonance. So when I now look at the bottom one, which of those two structures should I be comparing or being more critical with? I always want to form the most stable, so I need to be looking at the most stable one, which is this structure. If I compare that structure to the kinetic intermediate, ooh, interesting. It's a negative charge on oxygen in both cases. So charge doesn't help me, okay, because they're both negative. The atom electronegativity doesn't help me because, or size doesn't help me because it's the same atom holding the charge, oxygen versus oxygen. Okay, electronegativity, no difference. What's the next one? Resonance. What does the bottom one have that the top one does not? Resonance. What does that resonance do? That makes the bottom one more stable, which then means intermediate number 1, whoops, happens to be our thermodynamic, and the kinetic happens to be the higher one.
Is this opposite from what we've seen in your videos?
Maybe. Okay. So if that's the case, we would expect, yeah, no, we can just run with that. Okay, and then the next step, what happens? Which one is more stable? The thermodynamic. So if we went through and added energy curves, okay, be careful drawing that. Which reaction would I expect? Thermodynamic. Is there ever a kinetic product? No. So something about my energy diagram I'm missing. What is that something? It's going to come down in this very, very first step, trying to decide, is there a difference in activation energy? Okay. Under the kinetic circumstances, we're using a really strong nucleophile. Very strongly negative. Where is that very strong negative going to naturally gravitate to? The very strong positive, which is going to do what to the energy of those two? When we take a look at the curve, okay, our thermodynamic, we look at our kinetic, that transition state is a little bit lower. Why? The nucleophile is going to strongly associate with that carbonyl carbon, lowering that activation energy, which then means now I have a way to differentiate between my kinetic and thermodynamic. Okay. How do I differentiate? You got an easy one. Begins with T. Rhymes with pure. What was that, Ree? No. T ends with per. Pure. Rhymes with pure. Temperature. There we go. I'm tired. That's why I'm saying that. Okay. What happens if we change the temperature? If I want the kinetic, what should my temperature be? Very, very low. Because if I have a lot of energy, what happens? The activation energy does not change, but I have enough energy to clear the activation barrier, right? Which then means I get the thermodynamic. If I remove that energy by keeping it frigid, I get very slow reaction because now we don't have a lot of energy to clear activation barriers. But the only barrier that can be cleared is the kinetic, and I end up with the kinetic product. So I can alter the temperature. How else can I alter this? Which I think might have been in the video. I think it was. Change the nucleophile. Okay, which product is formed first? Kinetic. Which product is formed first when it's hot? Kinetic. Which one forms first when it's cold? Kinetic. The kinetic will always, always form first because lower transition state, okay? Faster reaction. Okay? If we increase the temperature, what we're really saying is we're providing enough energy to do what to that first intermediate? Move it back to the reactant. When it's a reactant, what can happen? It could now go into the thermodynamic product. Because the kinetic is constantly in equilibrium, going to reactant and product, okay, it's constantly moving back and forth. But what about the thermodynamic? Because it is lower in energy, once I've cleared that activation barrier, can I reverse that reaction? No. Okay. So once the thermodynamic product is formed, it is now removed from the whole discussion, and I'm now left with that product. Okay. So we said we could tweak temperature. What else could we do? We can change the strength of the nucleophile. What does changing the strength of the nucleophile do? Let's start with a stupidly strong nucleophile, H-. What's our intermediate?
Kinetic.
What's our intermediate reactive thing? Look at our intermediate structure. Whoops. Here's our intermediate structures. What's the reactive structure? What's the reactive part in there?
Of the charge.
What charge? Yes? The negative oxygen. If I compare hydride to oxygen or oxide, which of those can stabilize the charge? Oxygen. How often will I find hydride by itself? Never. Okay, not easy to do. Which means, what is the distance as far as our energy between our intermediate and our reactant? That becomes massive. If that is massive, can I reverse the reaction? No. Which means the only product I can get is the kinetic. What if I switch to a different nucleophile? Say oxide. What is the relative stability of a red negative oxygen versus a purple negative oxygen? They're the same, which means the gap between those becomes nothing. Holy crap. Sorry. I'm going to just say that says nothing. That's good. Okay. Which then means I can reverse the reaction. So as soon as I form the kinetic, now what happens? Reverses back to the reactant. The reactant now has a second opportunity to make the thermodynamic product. Once the thermodynamic product is made, it cannot reverse, and I slowly kind of bleed all of the kinetic product away into the thermodynamic product. Okay? This is why equilibrium sucks. Okay, for those of you that watched that video, you guys' responses were all too serious about equilibrium. Usually my response is, oh crap. Okay. We've seen this before. We can use pKa's to determine which side is reactive, more or less reactive, so we can quantify it. The issue with using pKa's in this case, what did we say was our starting reactor, our most reactive starting material? It was the nucleophile, which happens to be negatively charged or a base. So is looking at the pKa's directly helpful? No, I kind of regret putting this slide in because I think it gets very confusing when looking at the pKa's, because you've got to do a lot of kind of back and forth between your actual nucleophile and its conjugate acid and doing all the kind of comparisons through it. Okay? So I would make the argument that unless you really, really want to, you should kind of ignore this and go based off the argument that we had already. If we have a hydride nucleophile and we produce an oxide intermediate, right, which way does the equilibrium favor? The oxide, because it's much more stable. How much more stable? Evaluate the pKa's. Okay? And that would say it's non-reversible. Okay? And that's kind of what this was attempting to do. Okay? So we can kind of briefly look at that. If we push this all the way to the end, we'd have a 15.7 pKa for the alcohol. We'd have to look at the conjugate acid to get the pKa of the nucleophile. So if we started with H- as our nucleophile, the conjugate acid would be H2. Okay. Because we're pushing our differences here, we end up flipping the pKa's on their head. This reaction is going to favor the side with the lower pKa because we've flopped from conjugate base to, or from the base to the conjugate acid. Okay, so I'm not sure how much I like how that's formatted. I would kind of ignore the references to pKa's. Okay, the important part is to recognize your comparison between the strength of your nucleophile versus the intermediate, which is a negative oxygen. That is your differential. If those two are equivalent in strength, which product do we get? Thermodynamic. If they are not equivalent, the nucleophile is way, way more unstable, we get the kinetic product. Examples, your textbook has a nice slide or a nice image, and they're using the term reversible and irreversible. Okay, and we did briefly talk about this. We have to be careful in what they're referencing. If we look at that very first one, oxide, okay, so we said our nucleophile comparison to our intermediate versus our intermediate, which is always O minus. We're comparing O minus to O minus. Okay, so in that very first step, okay, so we're going to erase all the irrelevant stuff, which is pretty much all of this. Okay, what would I expect the energy barrier to be here? Okay, the energy between my reactant and my intermediate. What should that energy barrier be if I'm comparing O minus to O minus? Nothing, which means reversible, which means I get the thermodynamic product. Okay? We'll always get the kinetic product. If I can reverse the reaction, I provide a second opportunity. That second opportunity will sometimes make the thermodynamic. But once I have the thermodynamic, I am now irreversible. Based off our equilibrium, I can't reverse back to forming the kinetic. Okay, so you have two equilibrium reactions, okay, bouncing off of each other. Okay, so we got a bunch of examples of our reversible nucleophiles, and we have a bunch of examples of our irreversible nucleophiles. Notice the irreversibles: sodium borohydride, H minus, can't stabilize a negative charge. Lithium aluminum hydride, H minus, same deal. Okay, the Wittig, what's the charge? Negative on carbon, can't stabilize the charge very well. Okay, the organolithium, negative on the carbon. Grignard, negative on the carbon. Okay? So if we put the negative charge on an atom that is not able to stabilize that charge, we would expect it to be irreversible, and we would expect the kinetic product to win out. Okay? Let's move over to the reversible category. Where's the negative charge on that bottom one? Carbon. Negative charge on the next one. Carbon. The next one. Oh, never mind. Sorry, I wasn't pointing at that one. Ignore me pointing at that one. I thought there was another one there. Okay, so let me draw the other one. Oh, I needed that line. And for the sake of brevity, where's the negative charge in this reagent? On our carbon, we have a copper. Copper is a metal. Carries typically a +2 charge. The lithium, that means our copper has to, or our carbon has to come in as a negative. Okay. Why is that now tricky? I said negatively charged carbons were irreversible if they're stupidly strong nucleophiles. Sorry. Why is the negative charge on, for those watching at home, this one not stupidly strong? There's resonance stabilization, and I'm really looking at the negative charge on oxygen. Okay, so that one makes sense. How about the next one? I'm going to kind of mildly pretend I didn't hear that. You're telling me resonance? Well, it didn't work that way. Well, maybe it works the other way. No resonance. Okay. So that one seems to be kind of a weird exception, except, no pun intended, what is special about that carbon? They were all negatively charged carbons. What is its hybridization? sp, which means it's become more electronegative, which means that negative is actually stabilized through hybridization and an inductive withdrawing effect from the nitrogen. Okay? Looking at the structure, would we then predict that? No, that is an after effect. We ran the reaction, oh crap, I thought that that was going to add irreversibly, and it added reversibly. Okay, why? Now I have an explanation why. Okay? Everything we do in this class, someone came up with a theory, tested it, and it failed, so they went back and said, oh, well, it must have done this instead. Okay? It is not black and white like it's presented. Okay? What happens with this last one? Okay? At least in these other ones, we had negative charges. We can kind of see where they're coming from, but this is a straight-up alkane. Okay? No hybridization effect. It's not near an electronegative element. In fact, it's near a positive, which means that methyl group should be stupidly negative. And yet, what do we find when we tested it? It's not irreversible, it's reversible. It does the 1,4 addition. Now that we know that, why would we say that? So let's see. Ignore that. Why would we now say, okay, now that we know the product we get is the 1,4, how can we go back and rationalize why that copper lithium reagent, or the organocopper lithium reagent, okay, is reversible? Okay, because the classic example to compare it to would be the Grignard reagent. The Grignard reagent was irreversible. What is the difference between those reagents that suggests the copper one is reversible? The metal. The metals are a big difference. It's copper versus magnesium. How does that change things? Charge, meh. Size, copper's potentially bigger. That could help stabilize the charge better. If it stabilizes the charge, what does it become? Reversible. Okay, that could work. What else? What's the next thing in our list? Electronegativity. Where's copper relative to magnesium? Farther to right, which means the copper is more electronegative, which means the difference between the carbon and the copper is not as much, meaning the carbon is more stable because it is less negative. So knowing the answer, we can come up with an explanation. Unfortunately, what do you get tested on? Knowing the answer outright. You don't get the benefit of doing an experiment. Okay? Questions? Okay. Because I got a headache. I'm sure you guys do too. Which product do you expect? Okay, so I asked two questions. Trying to decide which of the tautomers is thermodynamic, okay, and then is it reversible? The reversible is looking at the nucleophile. So our nucleophile in the first one is a negative carbon, which would suggest irreversible. Irreversible means kinetic product. Okay, before we look at the next part, or the answers, let's move on to the next one. What's the next one? Okay, we have a negative oxygen, and a negative oxygen is reversible, which means thermodynamic. Last one, a negative carbon, irreversible, and kinetic. So we at least know what we're aiming for. Now the question is, can we find it properly? Right. If we look back, which I'm not going to move back because I already wrote stuff on this, okay, but if we looked back, we were comparing the stability of the pi bond. The pi bond that was what functional group? It actually was not a carbonyl. We were looking at the alkene. When we look at these two products, do we have alkenes to compare? No. It's actually hidden. That was our enol that then did what? Tautomerized to the carbonyl. So if we clean that up and take our carbonyl and make sure that it's drawn out now so that we can do a fair comparison. And the first one, which is our more stable, which is our more stable product, left or right? The left, because more substituted.
Could you also make a steric argument?
Don't do that.
Yeah,
So that is your more stable. Which product did we want? More stable meant what? Thermodynamic. Which product did we want? So we've identified this one as our thermo, which means the answer one, the other one's our answer. The answer one's our other. How about the next one? This is our stable. This is our thermo. Oh, look at that. We were looking for our thermo. That needs to be the one we would circle. Next one. We're looking for a kinetic product. Again, the more substituted is our thermal or our thermo, which then means the left one's our answer. Okay. Are there questions on that? Because it sounded like there were a couple questions floating up.
We're doing practice problems in the book, and I thought maybe I just got them confused.
It's stupidly easy to get them confused.
I know that tautomer happens, but it only happens with one of the additions, like either.
It only happens with the
or the 1,4.
1,4. It only happens with the 1,4. The 1,4 is which product? The thermodynamic product. What did we just identify as being our thermodynamic product? The 1,4 addition. Okay. So which is going to be kind of the next issue that I'm going to address here. Okay. Do we have other questions on what's up there? Because I need to erase a bunch of stuff.
My question is, we We don't need to evaluate the temperature down in the third one. That,
The nucleophile will trump.
yeah. Even if it was like,
The nucleophile will trump.
okay.
You have to really drop the temperature with your irreversible ones to be able to get it to work anyway,
What do you think?
because they're that reactive.
The thermo is a reversible.
So let's take a look at that second reaction. Here's a multiple choice. Okay, and for lack of creativity, your fourth answer says goats. Which is the correct answer? A, B, C, or D? That's an interesting answer, A and C. In our multiple choices, we do have the option for saying multiple things, but that is an answer choice. A and C are the answer. That's not an answer choice. Why is C the correct answer? C is the more stable form of our keto enol. Okay. Why does this become even further confusing? Let's take a look at C versus B, because those would be our primary structures. What was added in B? Identify the atoms that were added in B. OCH3, red's a bad color to pick. Let's try blue. That oxygen was added. What else was added? The H, where? On the OH. Those two atoms were added at which positions? 1 and 2. One was at whatever arbitrary position, however we want to number it, at position 1, and the other one's at position number 2 of our carbonyl. Okay. What was added in the second one, in answer choice C? Our oxygen was added, and a hydrogen. Where was that hydrogen added? Where is it? Where should it be drawn? On the alpha carbon. That product was known as what product? The 1,4 addition. Can someone please count for me how the blue hydrogen and the blue oxygen in structure C are located at position 1 and 4? Anybody? Yeah, you can't really pull that off. Okay. Where's the 1,4 addition actually happening? In the enol form. That's your 1,4 addition. The oxygen's position 1, 2, 3, 4. Okay. Yes, you can shake your head. I didn't invent it. I just found it.
Well, that is what happens when
It is. Yeah. And when you do it, that's what works, except when you look at the products, you don't see 1,4.
Yeah, essentially.
So it's hidden. The actual product for the 1,4 does not look like a 1,4 addition, but it is. Okay? Questions on that? Okay. Our Gilman reagents, okay, which we talked about, you're looking at that copper. If you see copper showing up with carbons, think Gilman reagent, put it as the 1,4. Do your thermodynamic products, just put it there. Don't question it, just do it. Okay. You could go through and look at some mechanism stuff for it, but it's not worth it. Just do it. Okay. Your textbook will break down the individual steps to make the Gilman. Okay, so you can see those in the textbook, because I don't think I've got it on the next slide. No, I don't. Okay. But it's what it is. You're going to end up seeing copper show up. So it's copper metal, just like a Grignard is with magnesium. It's the same general format.
So
Okay.
the 1,4 is the 1,4, right?
So yeah, if we look at this one, where's our 1,4 product? It's the one where the addition appeared to not happen in any way, shape, or form like a 1,4 addition. Right. The other one's a 1,2 because we're referencing the reactivity of the carbonyl. It's always back to the carbonyl in these cases. Okay? questions? Yay! Moving on. We're not going to do synthesis. I'm going to ignore that because we already talked about that. Chapter 18. So this is another one of those spider slides. And of course, formatted for a different textbook, which is why things are kind of cluttered and grouped oddly. But what we've talked about in Chapter 17 was pretty much everything on the left-hand side. You'll notice that I don't show any of the 1,4 additions there. It's just your standard carbonyl. And then we have oxygen and nitrogen reagents and all the little fun, stupid things that they can do. Okay. Why are they stupid and annoying? Because what do we have to look at? Equilibrium. Okay. So word association. What do you guys really think of when you think equilibrium? Gen chem? Balanced. Okay. It's a pain. It really is. Okay. So a lot of the things that we've talked about happen to be why does something happen? Okay. Or it's happy. It's more stable. Okay. We can't really use that argument when we're looking at a reaction that is strictly in equilibrium. Okay. We have to start using everybody's next favorite scientist that is in relationship to equilibrium. What was that? No. Le Chatelier. Remember all Le Chatelier's principles? How do you favor one side over the other? Add a whole bunch of one reactant, remove products, all that fun nonsense that you did in Gen Chem. That's what's driving everything in Chapter 18. Okay? So you can't look at it and say, well, oxygen holds a negative charge better than nitrogen, so oxygen is going to be the one that's negative. It depends on the concentration of everything else present in that reaction and where is concentration specified in your mechanism. It's not. You just have to deal with it. Okay? I'm sorry, but that's what you've got to deal with. Okay? Yeah, got to try. So the next part, this section is notorious for students breaking Lewis rules. Okay? Do not break your Lewis rules. That's why they're there. Keep your octets. Move electrons, okay, from a source to a lac. Never take electrons in a carbonyl and take the electrons and put them on carbon. Okay? I just said that, so let's take a look at what that is. We have a carbonyl. What's a carbonyl? Okay. Can't tell you how many times I see this thing happening. What's the problem with that? It's not going to happen because oxygen is more electronegative than carbon. I know what you're trying to do. You're trying to generate something that can make a structure further on down the line, but you are breaking Lewis theory rules. The instant you break Lewis theory rules, everything you do afterwards is wrong. Stop looking at it. Don't tell me, well, if I keep going 4 more steps, it'll work. No. Your first step was wrong. Okay? You can't make an argument on something that is wrong. So you have to go back and fix that. The biggest issue that is going to come out of this is these mechanisms are long. Not because we're doing chemistry long, but because we're doing stupid, obnoxious acid-base reactions long. You will put a proton at one point of the reaction, and 2 steps later, what are you going to do? Remove that hydrogen, and then you're going to put it back on 2 steps later. So why do I have to do that? Because that's how the electrons move. That's how it works. Okay? It sucks. Deal with it. Okay. So, water as a nucleophile. So here's a quick quiz. Where should the water attack? It should attack the alkene because this is a weak nucleophile, which means we're pushing our thermodynamic reaction. Okay. Why did I not have that shown? Because I wanted to attack the carbonyl. Okay. That's why there's no alkene. So, no alkene. Where is it attacked now? Carbonyl, carbon. What happens? We've exceeded the octet, so we have to push electrons up onto that oxygen. What would we end up with? Okay. Now what happens? Okay. I'm hearing a lot of people say this as well. Hydrogen leaves. No. Technically not. The action of leaving is reserved for something taking electrons. Oxygen is not taking the electrons. The hydrogen is not taking the electrons. The oxygen is, which then means hydrogen, at best, is removed.
Say kick out.
Okay. I would complain less about kick out. How about that? Okay. A lot of students don't like that mechanistic step. Why not?
You don't show.
I didn't show what picked up the hydrogen. Why not? Because something remotely basic in solution will pick that up. Like maybe a negative charge on another structure floating around. Or maybe just water itself will pick it up. Okay? The exact details of, that was accidental. The exact details of what picked it up, I really don't care. Okay? If you need to show it, by all means go ahead and do it. But that is your choice. Okay? So we could remove the hydrogen. In a second step, which I've screwed up here, what would need to happen? We need to protonate the oxygen. Jerk. Okay, we would need to protonate the oxygen. Where did that hydrogen come from?
Somewhere in this.
Again, I don't care. Somewhere in solution. Okay? It is out there somewhere. Okay? All that together, what we end up with at the very end is this structure. What is this structure known as? Whoops. A hydrate, because what did we do? We added water. That's it. It's been hydrated. Okay? Would we expect this reaction to work? Why not? Our very first structure shows a negative and positive. Okay. What happens when we have negatives and positives? They immediately react, typically with each other. That's a big mess. We can't form that. That structure is now stupidly high in energy, which means this reaction fails. So how could I improve it? How could I make sure that I get the product? Change the nucleophile. Change the nucleophile to what? Okay, so interesting that you use those word choices. I'm going to call you guys out on it, but thank you for participating. We add an acid. Where's the nucleophile? What's that? No? A positively charged oxygen will act as a nucleophile? Carbonyl oxygen, if it acts as a nucleophile, needs to react with anything other than hydrogen. What is that oxygen going to react with? The hydrogen. What is the result? Do I have a nucleophile in that reaction? No. Did I change the nucleophile? What's the next step? Electrons are going to move to the what? Oxygen is positive, which means the electrons in that pi bond need to move where? Towards the oxygen. Because the oxygen is more electronegative. That gives us a resonance structure on the positive carbon. That's still not the hydrate. What needs to react with it? A nucleophile like water. What was our nucleophile in the previous reaction? Water. Did we change the nucleophile? No. What did we change?
The order in which it happened.
We're changing the order, but by doing what? Why does that all of a sudden change the success of this reaction? So if I look at that next step, after my nucleophilic attack, what do I end up with?
Same product as before.
Do I?
Well, once you deprotonate it.
Once I deprotonate it, sure, but there's that intermediate. What is special about this intermediate?
It's more stable than the other one was?
is more stable because
It's only a positive.
it is only positively charged. Okay? By changing the reaction, I'm getting rid of one of those charges through the process of this reaction. What did I do to change it, though? Did I change the nucleophile? No, it's water. The nucleophile is exactly the same. Nothing happened to the nucleophile. What did I change?
Conditions.
What about the conditions?
We went from neutral to acid.
Why does that affect anything? When the nucleophile attacks, what am I attacking? The same structures I had before? No. What did I change? I changed the electrophile. The electrophile has been changed to being that positively charged carbon. Whereas before, what did we have? Whoa, go away. Just the carbon, okay? By protonating the oxygen, it's no longer a carbonyl, it's a carbonyl cation. The carbonyl cation is more reactive because it's positively charged. Okay? So we can alter the electrophile. That is probably the harder of the two. How do we alter the nucleophile? We need a stronger nucleophile. Well, what was the nucleophile in our reaction? The oxygen, good, coming from water. For that to become a stronger nucleophile, what do I need to do? I need to remove an H so that the oxygen becomes negatively charged. What type of chemistry happened in that reaction arrow? What do I need to add to get this reaction to have a stronger nucleophile? Killing me. We started with H2O. We're trying to make H2O OH minus. What do I need to add to make H2O OH minus? What did H2O do? It acted as an acid. So what should I add to the reaction? A base. Okay? Very careful, very methodical. Questions? Okay. We could go through and look at the mechanism. Boring. You should be able to figure it out. We've got the electrophile, making the electrophile more electrophilic by adding an acid. So you weren't right at saying adding an acid, but you weren't identifying what that did. That changed the reaction because it made the electrophile more electrophilic. Okay? That very first step, we added the acid. What did the acid do? Protonated the carbonyl. I now no longer have the carbonyl compound. I have a more active electrophile. I can use a weaker nucleophile. Can I have a strong nucleophile and a strong electrophile in these reactions? Why not? The water is acting always as a nucleophile, so I don't quite accept that. What if we had a strong nucleophile? What would it be? What did we say our strong nucleophile was? Say it louder, Sean. OH minus, yes. Okay. What was our stronger electrophile? The positive oxygen. And we got the positive oxygen by doing what? Adding a strong acid. Can I have a strong acid and a strong base in the same solution? No, they cancel each other out. So I have to pick one and stick with it. Notice that your mechanistic steps change. When we changed the nucleophile, it was done in 2 steps. Sweet. When we added the acid, it's done in 3 steps. We have an extra step. Okay? If you're going to go under acidic conditions, what charge should you never see in your mechanism? I'd say that again. If you're under acidic conditions, what charge should you never see? A negative. Because a negative is a strong base. If we're under acidic conditions, it can exist. If I'm under strongly basic conditions, what charge should I never see? A positive. Right? So you have to be careful when approaching your mechanisms to make sure that you don't ruin one way or another. We can drop it into energy diagrams. You can see the difference in energy because they went through and quantified it. Okay. I promise I'm about to stop. Our difference between what happened now, talking about carbonyl, and we reacted it with, what was the nucleophile? What's the nucleophile?
Oh, this, an alcohol.
An oxygen. Still the same nucleophile. It is oxygen. But is that oxygen water?
No.
No, that oxygen's coming from an alcohol. How does that change the reaction? Really, it doesn't. Okay. However, if we look at the product, that has 2 alcohols attached to it. That seems a bit weird. Okay. Those are 2 alcohols. Okay. That R group came from your alcohol. Yeah. What we are looking at is the formation of what is known to be an acetal. You will learn to hate acetals if you move into biochemistry, because that is a huge section of biochem, is looking at carbohydrate chemistry. Halfway there is the hemiacetal. We will talk about that again. Really what I want you to do is I want you to go through this synthesis, or attempt to go through this synthesis. Come on. Of starting with the carbonyl and making it to the acetal. Since we're doing the same thing we did with the hydrate, we can catalyze this reaction by doing what? Adding, I heard someone say it, base. What does adding the base do? Stronger nucleophile. Or we could have added acid, which would have done what? Stronger electrophile. Okay. The acid addition is already shown in the video posted online. You should go through and watch that. I'm sure you'll love it. Those of you laughing, I guess you watched it. What I want you to go through and do is show me how to do it under basic conditions. So we've made the nucleophile more nucleophilic. Okay. So today's Wednesday?
Yeah.
So Monday, what I want to see on the board, okay, is the full synthesis with the nucleophile synthesis, or with a stronger nucleophile. I want to go from the carbonyl to the acetal. Do what you got to do, because we want it up on the board so we can talk about it and look at it. If you got to cheat and use the textbook, fine. You got to cheat and delete the white boxes that are on my slide, fine. But I want you to draw it. Okay? And once it's drawn, we will talk about it on Monday.